So the work I'll talk about is joint work with my student Eric Lin, with Alejandro Carderera, who is a PhD student at Georgia Tech, and he works with Sebastian Pokuta, who is also co-author on these works, and I believe gave a talk earlier today, which I unfortunately missed because it's 8 a.m. where I am right now. Okay, and if you scan QR codes, you can also access the two papers that the talk is based on. So let's start with the problem setup. We are given a convex optimization problem that is a little bit of a special convex optimization problem, where the function we are minimizing is both smooth and strongly convex, which means that if you take any 2 points and you look at the linear approximation of the function, it is bounded both above and below by a quadratic. So the function is kind of nicely curved, but it's also not too steep. And the feasible set that we look at is a closed convex polytope, which I'm sure this crowd sees a lot as the feasible set. And in the setup, we assume 2 types of axes. First, the axis to the objective function is via first order oracle queries. So given any point from the polytope, you can get back the function value and the gradient. And the polytope itself is accessed using linear minimization oracle. So for any vector, you can solve a linear optimization problem over this polytope. Now, there are many examples where you would see a problem like this. The most obvious one would be just doing orthogonal projection onto the polytope, but also there are variants of Kara-Theodori problem. Sometimes people like to use the methods I'll talk about to solve different variants of LASSO, because you tend to end up with sparse solutions and so on. So the most basic method that is used in this setup is the classical Frank-Wolfe algorithm from 1956. The method is quite simple. So it is an iterative method. It has these step sizes, alpha k, and you can determine them using line search, but kind of the most standard choice would be to set them to 1 over k plus 2. There are also other values that would work, but this is kind of the standard one. And then what you do in each iteration is you query the gradient of your function, you minimize along this gradient slope, you find the minimum, which, without loss of generality, is a vertex of the polytope, and then you take a step in the direction of the point you found. Now, you normally would start from a vertex, and every time you add something to your solution, you're taking a convex combination, so this is guaranteed to remain within the polytope. Right? And it is a popular method. There are downsides to it that were actually noticed quite early on. And the downside is that the method converges at rate 1 over k, even if you have a really, really nice problem. Okay, even if you have just a quadratic function. Now, there has been a lot of work on improving the convergence of Frank-Wolfe methods, starting since at least the 70s. One way you improve the convergence is by allowing also to remove some of the vertices, because in the standard method, you may add the wrong vertex that takes a very long time to wash out. And that's what causes this 1 over k convergence rate. Now, some popular methods, and there are many, I'm just mentioning 2, are away step Frank-Wolfe and pairwise Frank-Wolfe, which use this idea. They can get what is known as linear convergence, meaning that the error contracts exponentially fast, but this constant here that you have in convergence, it depends on the geometry of the polytope, and it cannot be better than 1 over n, where n is the dimension. Now, this is kind of what things look like when you rely on linear minimization oracle. But if you look at the methods that are based on projections, so if you assume the stronger oracle access to the polytope, then you would get a much better rate of convergence. So here you would be contracting with square root of the condition number, smoothness over strong convexity. And yeah, so to get a point with error epsilon, you get root condition number log 1 over epsilon iterations. And the natural question to ask is, can we do this also with Frank-Wolfe type methods, where by Frank-Wolfe type methods, I mean you access polytope with linear minimization oracle? And the answer is kind of, it depends, yes and no. In the worst case, no, you cannot, and the global acceleration is impossible. And there is a known lower bound I'll go over quickly that tells us that if you're only relying on linear minimization oracle to access the polytope, then there's even a very nice function you can try to minimize, but the number of queries it would take you to get to optimality gap epsilon is the minimum dimension and 1 over epsilon. And let me just quickly tell you about the lower bound, because it's very easy, I would say. And so the problem instance for the lower bound is just the nicest quadratic you can come up with, condition number 1. The feasible set is just the probability simplex. So what you can say about this problem is that the optimum is going to be at the uniform vector, because everything is nice and symmetric, so it should be kind of direct. But now let's say you start from a vertex of this polytope. The only thing you learn in each iteration when you run a linear minimization oracle, at best, is another vertex. So after k iterations, you have uncovered k vertices plus the one you started with. So you have k plus 1 vertices. You don't know what the rest of the feasible set looks like. So the best you can do is just to choose a uniform vector over those k plus 1 vertices. But if that's the best you can do, then your error or optimality gap after k iterations is at least this much. And now if you look at error epsilon, this is what will bring you to this bound. Okay, it's kind of not the most robust lower bound, but it tells you kind of what is going on. So where does the difficulty really come from? Well, in this example, it is just that we have a very dense representation of the optimum in terms of the vertices, and we can only discover one vector from this representation. But what you can also here,
can I have a quick question? So, I mean, you could with the linear optimization oracle do some separation and other things, no? I mean, does this preclude those also? I mean, is it obvious that, for example, I could do unconstrained minimization within the for some while, and then I get to some point and I say, okay, wait, maybe I'm not in the polytope, and I can use the linear optimization over the polytope to sort of like separate something and then do something else. So, I mean, this lower bound is simply saying if you just use in a very naive way, you can't do it.
Yeah, that's a fair point. But I haven't seen much about how using a membership oracle or a separation oracle would help you much in this case.
Yeah, it may not, but it's not obvious that it could.
Because yeah, so for example, as we'll see later, your optimum may lie on the face of a polytope. So if you're just running naively unconstrained optimization, well, I mean, even in this example, how would you run unconstrained optimization? Because your feasible set is the simplex. So you take any gradient step, you're going to step out.
Yeah, let's take it offline. I just am curious. So the lower bound is robust.
Yeah, it's not the best of lower bounds, but what it kind of illustrates is that essentially in this model, you just may need to learn many vertices to get a reasonable solution. And really from Karasidori's theorem, order n here is really the worst case. So on some nice polytopes, you could hope to do better. And there is a question also, once you learn enough about the polytope, what happens then? Because the lower bound doesn't really tell you anything about that. And in particular, can you then get this accelerated rate? And we show that the answer is yes. So after some finite burning time, then you can actually get this nice accelerated convergence. So this phenomenon of having a burn-in and then doing acceleration is what we call local acceleration. Now, let me give you just a super basic idea that you could start with, and it actually starts from what Chandra just mentioned as the initial idea, something that you could hope to try. And because we are here assuming that the function is strongly convex, it is curved. So what this tells us is if we are improving in terms of the function value, then we are also guaranteed to get closer to the minimizer. In other ways, like your iterate cannot lie arbitrarily far from the optimum. If you're making function value small, this distance must also be getting smaller. And this just comes from strong convexity of the function. Now, the first idea you could try, and then it's exactly what Chandra was suggesting, is you take, well, not maybe exactly, but it is in that spirit. You can run any Frank-Wolfe variant, and you run unconstrained Nesterov in parallel. Now, if your optimum lies in the interior of the polytope, you know that after some time, you are going to land, while running Nesterov, you're going to land inside the polytope, and you're going to land kind of close to the optimum solution. So what you could do is every once in a while, you check whether Nesterov's output is in the polytope. If it is outside, you could restart the method and initialize at this Frank-Wolfe variant. It will place you back into the polytope. So if you're lucky and your solution happens to lie in the polytope, eventually you're going to start converging at this accelerated rate. Okay, so this works for this particular setting, but there are a few downsides. One is that you need stronger axes. You do need membership oracle for this to work. And this only works if you actually have a point that is in the interior of your polytope. So the question is, can we generalize this further? So not only when the point is in the interior, but maybe it is in the interior of a face. So we can still get local acceleration. The case is always that you can assume that you're constant deep inside the face. If you're at a vertex, Frank-Wolfe would work already. So really when this will not work would be just some degenerate cases where you have kind of really spiky polytope. So the new strategy now is that you run an active set-based Frank-Wolfe variant. Active set is just the set of vertices that represent the solution so far. And you run a constrained variant of Nesterov or another accelerated method, doesn't matter. And you run these two in parallel. So what you do is every once in a while, you stop and you compare the function value for the Nesterov and for this away Frank-Wolfe. If away Frank-Wolfe gives you a better point, you restart Nesterov, you initialize it at this output point of away Frank-Wolfe, and you take the feasible set of Nesterov to be the convex hull of the active set. So in this case, the away Frank-Wolfe point is represented by these three vertices. So this would be now the feasible set of Nesterov. And at any point, if you want to output something, just output the better of the 2 points. So this cannot be worse than away Frank-Wolfe. And you would hope that you would get acceleration eventually. And what is needed is that after a while, the active set actually contains the optimal point. And you know, this doesn't take forever to happen, but after some finite time. And there's a tricky part that I'm not mentioning here about restarts. So this requires technical work, because if you restart too often, you can actually mess up the convergence of Nesterov. You need a sufficient number of iterations to actually get the contraction that you need. And but you also don't want to do it too infrequently, because then you may fail to switch to a good feasible set. So that's kind of where most technical work happens. And we show that actually you can do this. So we provide a structural lemma that guarantees that after a finite burn-in that depends on the geometry of the polytope, but not on the target error epsilon, you're guaranteed to have the optimal point within the convex hull of the feasible set. And there is another ingredient that we need to use a monotonic variant of accelerated method. We need to also support inexact projections and other stuff for everything to kind of check out. So what you end up with in terms of the number of iterations, each with constant number of oracle queries to the function and to the linear minimization oracle, it will look like this. So you'll have some finite burn-in, excuse me, that's independent of epsilon, and then you're going to get this accelerated convergence. And let me just illustrate what this coupling looks like. So you could start from a vertex. So initially the accelerated point and the away Frank-Wolfe are the same. You run them in parallel. You know, the accelerated point is not going to move because its feasible set is the vertex. Whereas away Frank-Wolfe is going to move and add points. Then you restart and you run into a new feasible set, and then you do another restart. Now you're at the optimal phase, and the accelerated point kind of moves faster, right? So even though you're doing a bunch of stupid things before you reach the right phase, eventually you're going to get to doing the right thing. And now you could be wondering, like, okay, you know, this is all a nice story, but is it just like a theoretical curiosity, or do we actually see this local acceleration in practice? Well, we implemented this, and it turns out you do. So this is one example, just a quadratic on a Birkhoff polytope with 40 nodes. So this is away Frank-Wolfe. The red one is if you did black box acceleration. And this is our method that does local acceleration. And now the iterations are more expensive. So you could say, oh, in terms of time, I still wouldn't gain. It turns out you would, because the convergence is so much faster that you actually do see it also in terms of time. And that may seem like, okay, that's not a real example. we could have cooked it, but here is an example with real data and actually even more algorithms. So black box acceleration, away Frank-Wolfe, pairwise Frank-Wolfe. So these are all standard. You can actually couple our method with either away Frank-Wolfe or pairwise Frank-Wolfe. This is what happens in terms of iterations. You see local acceleration, and even in terms of time, you know, even though the iterations are more expensive, you still manage to beat the other methods. So now the main downside of this method is that it is not parameter free. So I swept this under the rug, but to determine when to restart, you actually need to know this smoothness parameter and the strong convexity constant. The smoothness parameter is less of an issue. There are standard ways, such as backtracking line search, that can help you get away with not knowing it. Strong convexity is more of an issue. It is harder to estimate, and yeah, so what do you do? If you get the wrong strong convexity constant, you're also going to get a much slower method. So what we did next was come up with a variant that does not require this knowledge. So let's start just with an easy case as a warm-up. So let's suppose you knew the minimum function value. And there are even examples of that, like take a Carathéodory problem where you're given a point from the polytope and you want to find the set of vertices whose convex combination gives you that point. You want to find the smallest such set. But kind of a practical approach to solving this is typically using Frank-Wolfe methods, where you take the convex combination of the vertices and you're minimizing this function over the simplex. So the reason you would use Frank-Wolfe is because it tends to add few vertices, so you tend to end up with kind of sparse representation, even if it's not the best one. So for this problem, because the point is from the polytope, we know that the minimum is 0. Okay, so what would we do here? So what I could do is do the same coupling as I did before. So we've run a wave Frank-Wolfe and an accelerated method in parallel, except that now I will restart every time that my optimality gap halves compared to the previous restart. And when I restart, I just kind of initialize at my output point. And then the coupling works the same way as before. So I look at the output of Nesterov. If the wave Frank-Wolfe is better, I initialize at that point and continue. Update the active set nodes. You can argue that this does work. And the total number of restarts will be log 1 over epsilon, right? Because every time you're just reducing your error by half. What you can also argue is that after a finite burn-in, when you get to this point where your feasible set contains the optimum, Nesterov is guaranteed to contract the optimality gap within order root L over M iterations. This works nicely. You don't actually need to know either L or M. But things get harder if you actually assume that you do not know the minimum. You cannot use this halving strategy because you don't know that, sorry, this should have been X star. You don't know that your optimality gap has halved, right? You cannot guarantee that you're making the right progress. You can think about using a different measure of optimality like gradients. This is a constraint problem. Gradients may not be 0. There are generalizations of the gradient, typically projection-based, that you can imagine using. There are technical issues to that too. 1, you do not have projections onto the whole polytope. 2, if you think about projecting onto these convex hulls of active sets, you update those every once in a while for the method to work. But every time you update, you wouldn't be guaranteed that your measure of optimality would go down because it depends on the set itself. So I don't know of a way how to argue that this would actually work. There is still a way to make it work. So you do the coupling, but now you restart every time some computable measure of optimality halves. So this is just kind of a high level idea. And you update the your point to the output point and to the right active set. It turns out that this measure of optimality that we use is not a real measure of optimality everywhere, but kind of when you get close to the optimum, it works. So it requires technical work to actually show that it works, but it is possible. I just want to give you kind of a high level of the high level idea of what happens. And there is parameter-free variant of Nesterov that you can use in between these restarts that makes the whole thing go through. The runtime becomes a bit worse. So we still have this finite burn-in that's independent of epsilon, depends on geometry of the polytope. But now, in addition to this accelerated convergence, we get some extra 2 log factors. The log factors don't have epsilon, but they have, so this d over delta is the part that depends on the polytope. Other Frank-Wolfe methods would have polynomial dependence on this, actually. So I'd say it's not that bad. And before I wrap up, let me show you more numerical experiments now for this parameter-free variant. So here is an example for LASSO, where we also added some linear constraints. There are reasons why to do this that come from physics applications that Sebastian would know about. So a wave Frank-Wolfe, pairwise Frank-Wolfe are method when coupled with either of them. So you can see that at some point this local acceleration kicks in, and the iterations are now more expensive. So in the beginning, you may see kind of worse convergence, but eventually you do become faster, even in terms of time. And here is another example just on Birkhoff polytope, maybe not as dramatic of improvement, but this local acceleration is still there. Okay, so to summarize, even though it's not possible globally, in this case, it is possible to achieve this local acceleration, and kind of the broader message that, it's obvious to all of you is sometimes you need to open the box, and it helps to look at the problem a little bit closer instead of just focusing on the worst case. And the phenomenon I've shown you is not just theoretical curiosity. You can observe things like this also in the experiments. Some open questions. The first one, the lower bound is not particularly impressive. Can we actually get a better lower bound that would also capture what happens after this finite burn-in, and that holds against randomized algorithms, arbitrary starting point, and so on. And we only address this case when the function is strongly convex. You can generalize it to other things, when the function is sufficiently curved, like things like sharpness, but we need some sufficient curvature. Otherwise, this burn-in would become very long. And it's an open question to see whether you can get local acceleration for general convex case with burn-in independent of epsilon. Okay, so thank you very much, and I'm happy to take any questions.